Hello, everyone. Let us now continue our discussion for perfect gases. Note that Boyle's law, Charles' law, and Avogadro's law apply only when two of the state variables are held constant. So it would be more convenient to combine these three laws into a single equation, which would be applicable to a more general condition wherein none of the variables are kept unchanged. So this equation would relate all the state variables of a gas and is called an equation of state. So the equation of state, which becomes very accurate as the pressure decreases, could be coined as described as limiting law, which increases in validity as P is approaching zero. So take note that the limiting law is strictly true at a particular limit. Now, each substance is described by an equation of state, which correlates the variables describing that state. For example, for a perfect gas, volume is a function of pressure, temperature, and the number of moles. Now, if we would take the total differential of volume to express the change in volume accompanying a change in pressure, temperature, and the number of moles, so would be obtain dV is equal to partial derivative of V over partial derivative of P dP at constant T and N plus partial derivative of V over partial derivative of T dt at constant P and N plus partial derivative of B over partial derivative of N dN at constant P and T. So take note, from Boyle's law, PB is equal to proportionality constant. So if we will take partial derivative of B all over partial derivative of pressure with respect to constant T and N, so this is KT multiplied by negative 1 times P raised to negative 2 or negative KT over P squared. So substituting KT as negative PB, negative KT equal to negative PB. So P would be cancelled out. So this is equivalent to negative V over P. So from Charles' law, volume is equal to proportionality constant multiplied by temperature. So if we will get partial derivative of V over T at constant P and N, so this is equal to Kp, simply saying V over T. And then from Avogadro's law, partial derivative of B over partial derivative of N at constant P and T. So this is equal to Kp or equal to V over N. Now, if we would substitute these three terms here in our first equation, from the equation of state, dV is equal to negative V over P dP plus V over T dt plus V over N dN. So since we have volume in each term and then combining this with dV, dV over V is equal to negative dP over P plus dt over T plus Tn over N. And you know that upon integration, the expression becomes ln V is equal to negative ln P plus ln T plus ln N plus ln R. So combining the terms, ln V is equal to ln nRT over P. So volume, or removing ln, V is equal to nRT over P. So therefore, PV is equal to nRT. So we call this ideal gas equation. So this is the equation of state of gases that is very useful, and it will be employed often to express one of the state variables in terms of the other variables. So the term ideal refers to the gases rather than to the law. So ideal gas is defined as a gas whose behavior is in accordance with this equation. Now take note for experimental condition, STP at standard temperature and pressure. So the molar volume is equivalent to 22.414 cubic decimeter per mole. Temperature is 0 degrees and pressure is 1 atmosphere. SATP or standard ambient temperature pressure. So this is equivalent to 298.15 Kelvin and pressure equal to 1 bar and occupies a volume of 24.789 cubic decimeter per mole. So again, if we will combining the three basic laws, Boyle's law, PV is equal to constant, Charles' law, V over T is equal to constant, P over N equal to constant for Avogadro's principle. If we will combine this into a single expression, PB is equal to constant multiplied by NT, we also call this nRT. So again, this is the perfect gas equation, which becomes very accurate as pressure becomes lower, as pressure decreases. So a real gas behaves like a perfect gas, though we will be discussing real gases in the next topic. So this could be pictured as perfect gas in the low pressure limit. So I mentioned this earlier. So the values for SATP as well as for STP, standard temperature pressure. Now, let us solve an example of the combined gas law problem. A gas sample has a volume of 20 cubic decimeter at a temperature of 30 degrees and a pressure of 90 kPa. So if the temperature of this gas is changed to 20 degrees Celsius and its pressure is increased to 250 kPa, what would be its final volume? So substituting V1, values of V1, T1, P1, as well as V2, T2 over P2. And we are after V2. So V2 is equal to P1, V1, T2 all over P2 times T1. So substituting V2 is equal to 6.96 cubic decimeter. Now, for R with different units, one of the common values of R is 8.314 joule per mole Kelvin. So this has been derived in terms of STP. So if you substitute pressure as 101.3 kPa, volume as 22.4 cubic decimeter, temperature as 273.15 Kelvin, so you'll get 8.314. Sometimes we are using 0.08 to 0.05 liter atmosphere per mole Kelvin. And take note that R is related to Boltzmann constant K, wherein R is equal to K multiplied by Avogadro's number. So this describes the surface of states. So the perfect gas equation can be represented as a three-dimensional surface of possible states. So meaning that a gas cannot exist in states not on the surface. So this represents the surface of possible states. So combining different conditions of pressure, volume, and temperature. So PB represents the isotherm. So if you will be referring to this point, and this line, so this is the isobar. Now, ideal gas equation could also be used to solve for the unknown molar mass of the gas. So this can be manipulated to derive an expression which involves molar mass. So you know that PB is equal to nRT. So N is equal to mass over molar mass multiplied by RT. So interchanging V and molar mass, P multiplied by molar mass is equal to M over V RT. And you know that this is equivalent to density. So if you're after to solve for the density of gas, density is equal to pressure multiplied by molar mass all over RT. And density of the gas is affected by pressure and temperature. Now, let's solve one example. Find the density of the fluorine gas at 20 degrees Celsius and 188 torr. Now, the pressure in torr, so we convert this to atmosphere, so divided by 760, so this is equal to 0.247 atmosphere. So the molar mass is 19 multiplied by 2, so since this is diatomic gas, 38 gram per mole. Temperature is equal to 293 Kelvin. So density is pressure multiplied by molar mass divided by RT. So substituting, so atmosphere will be cancelled out as well as number of moles as well as Kelvin. So density in gram per liter is equivalent to 0.39. or 0.39 gram per cubic decimeter. Now, this equation could also be used to solve for the molar mass of the gas. So in this problem, the molar mass of a known volatile liquid was determined using the Dumas method. So when we say Dumas method, so this is one of the classical methods for the determination of the molar mass of a volatile liquid. In this method, the liquid is placed in a small container, let's say a Dumas bulb or flask, and then vaporized by heating to a known temperature above the boiling point of the liquid. As the liquid vaporizes completely, the air in the vessel is expelled out and only the vapor occupies the container. So thus the system is then cooled to condense the vapor into liquid. The weight of the liquid is measured and the volume of the vessel is determined. Now, given the following, so mass of the empty flask from the experiment is equal to 65.347 gram. Mass of flask with the condensed liquid is 65.739 gram. Mass of flask filled with water at room temperature, so this refers to the volume of the vessel, could be represented because this is filled with water at room temperature, equal to 327.4. Atmospheric pressure is equal to 743.3 torr. The temperature is equal to 99.8 degrees Celsius, and density of water is equal to 0.997 gram per ml. So by difference, we could get the mass of water. So mass of water plus flask minus mass of empty flask. Then the mass of the condensed liquids, same formula. So to get the molar mass of the gas, so this is the mass of the condensed liquid multiplied by R, multiplied by T, all over pressure times volume. The volume here is represented by density of the density of water, 1 gram per ml, then converted to liters, so 262.053 times 10 to the negative 3 liters. So substituting, we'll get the molar mass equal to 46.8 gram per mole. Now, another famous law when we are talking of gases is the Dalton's law. So Dalton's law is also being used to describe the law of partial pressures in chemistry. So when we have a mixture of two or more gases, so the total pressure exerted by a homogeneous mixture of gases is equal to the sum of its partial pressures. The partial pressure of the gas is the pressure that it would exert if all the other gases in the mixture were absent. So let's say we have two gases in the vessel, A and B. So the partial pressure of gas A could be represented by PA, and the partial pressure of gas B is represented by PB. So the total pressure is equal to PA plus PB. So thus the partial pressure of A could be equal to NA/RT all over B. So in terms of mole fraction, you know that for mole fraction, this is the amount of number of moles of each gas all over the total mole. So you know that the sum of the mole fractions is always equal to 1. So thus, a partial pressure of a certain gas could be formally defined as mole fraction multiplied by total pressure. So, or get the partial pressure of each, then this is equal to total pressure. So let's solve one problem. A 10 cubic decimeter flask contains 0.2 mole of methane, 0.3 mole of hydrogen, and 0.4 mole of nitrogen at 25 degrees Celsius. So what's the total pressure inside the flask? And what's the partial pressure of each gas in the mixture? So to solve, the sum of the moles of the three gases is equal to 0.9. Let's get first P total. P total is equal to N total multiplied by RT over B. So substituting, you will get P total equal to 2.2 atmosphere or 223 kilopascals. So since we have three gases, let us try to solve one partial pressure. So let's take methane. So the partial pressure of methane is equal to the mole fraction of methane times P total. So substituting 0.2 all over 0.9, so this is unitless, mole over mole would be cancelled out, multiplied by 223 kilopascal, so you'll get 49.56 kPa as the partial pressure of methane. So you could do the same thing for the last two gases. Now, another is the average molar mass problem. A gas mixture is composed of 2 moles of H2 and 1 mole of N2 or nitrogen. Calculate the average molar mass of the gas and the density of the gas mixture at 273 Kelvin and 1 atmosphere. Now, in getting the average molar mass of a gas, so this is equivalent to the mole fraction of each gas multiplied by the molar mass of that gas plus let's say in this case we have two gases H2 and N2. The average molar mass is equal to mole fraction of H2 multiplied by molar mass of H2 plus mole fraction of N2 multiplied by molar mass of N2. So substituting, so 2 over 3 or 0.667 times 2. So this is diatomic molecule plus 1/3, 0.333 multiplied by 28 or 14 times 2. So the molar mass average is 10.67. So since it's a mixture of gases, we will be substituting this average molar mass to get the density. And the density is equal to 0.476 gram per liter. So recognize that if 1 mole of gas mixture is considered, the mole fraction gives the number of moles of each component in the gas mixture. The product, mole fraction multiplied by molar mass, is actually the mass of each gas, and the sum of these products gives the total mass of 1 mole of gases, or the average molar mass.